Hi, this is Tzvi Rosen. Welcome to another lecture in our series on the history of calculus. In this lecture, we'll talk about Madhava, an Indian mathematician from the school of Kerala, who published the first series approximation for sine and cosine. First, let's talk a bit about mathematics in ancient India. The earliest extant manuscript of mathematical writing from India is the Bakshali manuscript, and carbon dating places this either in the 3rd century or the 10th century, and it's a 70-leaf textbook full of algorithms for common computations, and it uses the decimal place system, which was definitely advanced for that time. Another early Indian mathematician was Aryabhata in approximately 476 to 550 CE, and he wrote a work called the Aryabhatiya, in which he worked on Diophantine equations, trigonometry, astronomy, and more. A bit later, we have Brahmagupta, who lived from approximately 598 to 668 CE, and his book was the first recorded treatment of 0 as a number in its own right. Earlier, you had 0 showing up as a placeholder, analogous to how we use 0 in the number 100 to signify that there's only the second power of 10 and no first powers and no 0th powers. But Brahmagupta's work was the first time 0 was a number in its own right. And then we'll zoom forward in time to look at the Kerala School of Astronomy and Mathematics. And Kerala is a region in the south of India, as indicated in this map. And there was an incredible school there, founded by Madhava of Sangamagrama in 14th century. One of the main accomplishments of the mathematicians in this school was to publish series expansions for sine and cosine before their European counterparts. The original publication of those series was in a book called the Tantra Sangraha, and that was without proof written down. But the proof was recorded by Jyestadeva in 1530, and he attributes the proof that he writes there to Madhava. Before we get into what those expressions are, what those series expansions are, let's think about how we would derive a series expansion for sine and cosine, just using our skills from the second semester calculus course. So Taylor's theorem says that if you let f of x be a k times differentiable function of x in a neighborhood of a, then you can write a series expansion for f as f of x equals f of a plus the first derivative of f at a times x minus a plus this general form of term up to k, where you have the kth derivative of a divided by k factorial times x minus a to the k. Okay, and then you have this remainder term, r of x times x minus a to the k, and r of x approaches 0 as x approaches a. So you have greater than kth ordered convergence of the remainder to 0 in a neighborhood of a. So looking at this theorem and remembering how we compute derivatives of sine and cosine, so the derivative of sine is cosine, derivative of that is minus sine, derivative of that is minus cosine, and of course that circles back. Okay, so to write down the series expansion of sine and cosine, we would take sine of x is equal to the value, and we're centering ourselves at 0. Okay, so a equals 0. We would have sine of x equals 0 plus cosine of 0, which is 1, times x minus a, so that's just x for us. And then we would have minus sine of 0, so that's 0 again, divided by 2 factorial x squared. Okay, and then we have minus cosine of x of 0. That gives us minus 1 over 3 factorial x cubed plus 0 over 4 factorial x cubed, etc. And let's do one more, plus 1 over 5 factorial x to the 5th. Okay, and that would continue out. And just collecting the non-zero terms, we would get x minus x cubed over 6 plus x to the 5th over 120, etc. Okay. As for cosine, using the same approach, we would have 1 plus 0 times x. Okay, since minus sign is 0, then we have minus cosine gives us minus 1 over 2 factorial x squared plus sine of 0 over 3 factorial x cubed plus cosine of 0, which is 1 over 4 factorial. I'm sorry, this should have been x to the 4th. X to the 4th, and etc. And this gives us 1 minus x squared over 2 plus x to the 4 over 4 factorial, which is 24, etc. Okay, so that's how we would get these series expansions, just knowing how to take derivatives and knowing Taylor's theorem. But obviously, Madhava did not have these results in hand, so he took a more geometric and quite clever approach. So you start by working on a unit circle, and you're trying to compute the sine and cosine of an angle theta. You break down that angle into n pieces, and you approximate the change in x and y as you move up your circle, and the formula you're going to write is in terms of the y values of those points. And you're going to approximate those y values using a first order approximation, that the y value is approximately equal to the angle. Then we'll express our total y value, our sine y, as a sum of these delta ky's, these changes in y, and take the limit as n goes to infinity, because n was how small we're breaking up the angle. So as n goes to infinity, we're adjusting our formula more and more times. So we'll get a new approximation and a better approximation, f1 of theta. And then we'll iterate. So just as we approximated yk with f0, our first order approximation, now we'll use this next approximation for the yk and get a refinement of our formula. That's the general approach, and let's see it in action. Okay, so here we are in the unit circle, and we're working on, and we're breaking down this angle into n parts. Okay, so we start with 1, 0 over here. Now we have the first point x1, y1 off of the x-axis, and we're going to call the change in y will be delta 1 y, and the change in x will be delta 1 x. You'll notice almost all of the change at this stage is in the y direction, because the circle is, or the vertical is tangent to the circle at that point. Okay, and then and actually I believe we'll call that delta 0x. We have a shift in the indexing, which seems to be necessary for the way that this computation is done, but it's not clear to me why it works quite that way, but we'll take that for granted. And so this angle is delta n of y, while this angle is delta n minus 1 of x. Sorry, this interval. So these are the distances we're looking at. These deltas are the change that we're applying to the x and y value as we move along this angle. Okay, so intuitively, this x is going to be x0 plus all of these changes in x, or really minus all of these changes in x, minus delta 0x minus delta 1x delta n minus 1x, and y is going to be equal to y0, okay, and this is x0 is 1 and y0 is 0, plus delta 1y plus delta 2y up to delta ny. Okay. That's our strategy. We're going to get really good approximations for these deltas and use those to get better formulas for the x and y. Okay, and one tool that we're going to use is the similar triangles in this image. So if we have a point xy that we're trying to understand, and it's in the middle of an interval with xk minus 1, yk minus 1 on one side, and xk, yk on the other side, what we have is two similar triangles. And you can convince yourself that that's the case by the fact that the green line over here is perpendicular, is parallel to a tangent to the circle, so it's going to be perpendicular to the green edge over here coming at it. And that allows you to establish a similarity of the triangles. So what that means is that we want all of the corresponding color edges to have the same ratio. So let's first determine what these side lengths are. Well, this red side is delta ky, and this red side is x. This blue side over here is delta k minus 1 x. Again, there's the shifting I mentioned. And this blue edge is y. As for the green, this is just 1. And the other green edge, because it's so close to an arc of the circle, and it will continue to get closer to that arc as the angle gets broken down smaller and smaller, we're going to call that alpha for the arc length. Okay, and you can think of this as basically theta over n. Okay, so what are we learning from this picture? Well, all of the ratios have to be the same. So delta ky is to x, as delta k minus 1x is to y, as alpha is to 1. Okay? And that's the equation that we're going to take moving forward in this computation. Okay. So first we'll work on getting formulas for delta kx and delta ky in terms of yk. And we want to note again that there's this shift. Delta ky is yk minus 1, while delta kx shifts up, so it's xk plus 1 minus xk. Okay, so here's the equation from the previous page. And what we do is multiply the first part of the equation by x and put it over here, and then we approximate x by xk. Okay, so there's this kind of implicit approximation that x is close to xk. Okay, and then there's this equation over here, that goes here, just multiplying by y, and then making the approximation that y is close to yk. Okay? So now let's see what happens. Let's see what happens if we take differences of consecutive delta ky's. Well, delta ky minus delta k minus 1y, using the equation above, you get alpha xk minus alpha xk minus 1. Okay? But that's just alpha times delta k minus 1x. Right? I'm just looking up at the formula for what delta jx is. Okay, and we have this formula for what delta kx gives you. So we end up with delta ky is equal, delta ky minus delta k minus 1y is equal to negative alpha squared yk minus 1. Okay, well that's nice, but then we can try to establish a tool for an induction by approximating delta, or by getting an equation for delta ky in terms of the rest of the stuff. So delta ky is equal to delta k minus 1y, just by adding to both sides of the equation, minus alpha squared yk minus 1. Okay, so I mentioned induction. Let's inductively compute a number of these delta ky's. So delta 1y, just plugging into the equation, you have delta 0y. That's going to be the same as, delta 1y is the same as y1 minus y0. And that's explicitly y1 because we know y0 is 0. Okay, so here we haven't used this equation yet. Okay, but then we use the equation in the following step. So delta 2y is equal to delta 1y minus alpha squared y1. So that just take the y1 from the previous line and replace it the delta 1y. Okay, same thing in the next line. We have delta 2y minus alpha squared y2. Take the previous line, subtract alpha squared y2, and you get this new expression, y1 minus alpha squared times the sum of y1 plus y2. You keep doing this inductively, you'll see that you're just getting sums of y1 up to yk. And the final difference is delta ny is equal to delta n minus 1y minus alpha squared yn minus 1, and that's y1 minus alpha squared times the sum of all of the y's up to yn minus 1. Okay. Cool, so that's a useful formula to have. And now we also want to pay attention to, so what formulas are we paying attention to? We have this formula, I'm going to switch this to yellow. This formula for delta kx, and this formula for delta ky. Okay? And let's take that forward to approximate x and y. So we saw before that x is equal to x0 plus the sum of these delta kx's. Here we're assuming that these deltas are negative. So these are negative. Okay, and indeed, so we have the value for delta kx from the previous page. It's minus alpha yk. Just plug that in for all of these values. And then factoring out the minus alpha, we get 1 minus alpha times the sum of all the y's. Now, if we approximate yk by k theta over n, okay, because again, that's our first order approximation. It's not going to be a great approximation for the y value if you're moving up the angle, but for small values, it'll be close and it'll get progressively worse. So we're setting yk equal to k theta over n, and alpha will be equal to y1 because alpha is that arc length, and so y1 will be approximately the arc length of one segment. So now plugging that in here, just plugging all those values in, we get x equals 1 minus theta over n times 0 of the first term, and we could really just drop that, plus theta over n for y1, plus 2 theta over n, plus 3 theta over n, etc., up to n minus 1 theta over n. And if you factor out the theta over n, you're left with 1 minus theta squared over n squared times a sum of integers. And this is a sum of integers that we know how to compute, whether by discrete calculus or thanks to Ibn al-Haytham. And we get this formula that x equals 1 minus n times n minus 1 over n squared, theta squared over 2. Okay? And we will be taking a limit, but not yet. Okay, well, how about y? So we know that y is equal to the sum of all of the changes in y, since we start at y equals 0. So plugging in the values we computed earlier for these deltas, we have that the y is equal to y1 plus y1 minus alpha squared y1 plus y1 minus alpha squared y1 plus y2, etc., up to y1 minus alpha squared times the sum of all yi's. So now we group together all of these guys and get n times y1. Okay. Then we group together all of the terms that have a multiple of minus alpha squared, and we get this summation. Okay, so working with this summation, we do something similar to what we did with the x. We plug in yk is approximately k theta over n, and alpha is y1 or theta over n. Okay, so we get theta minus theta squared over n squared times this summation, just again replacing yk by k theta over n. And if we factor out theta over n, we get theta minus theta cubed over n cubed times this sum of sums of integers. But this might be familiar from the equation of Ibn al-Haytham. So his formula said that n plus 1 times the sum of I to the k is equal to the sum of I to the k plus 1 plus the sum of p, from p equals 1 to n of the sum from I equals 1 to p of I to the k. Okay, so using that formula and setting k equal to 1, okay, then we move this, we subtract this to the other side of the equation. Okay, then we get, and we also have to shift these indices. Okay, but we get that the sum from the previous page, this sum of integers here, that this is equal to this difference of sums that are probably a bit more simple to compute. Okay, so what are we left with? Y equals theta minus theta cubed over n cubed times that sum is equal to theta minus theta cubed over n cubed times this difference of sums, n times the sum of k's minus the sum of k squareds. And we have formulas for each of these from Ibn al-Haytham as written here. And if you do out the math, what you end up with is theta minus theta cubed over n cubed times n cubed minus n over 6. And distributing, we get theta minus theta cubed over 6 plus theta cubed over 6n squared. Okay, so great. So we have formulas for x and y in terms of n. Here's the formula for x. And here's the formula for y. Oops. Okay. And now let's take the limit of these two formulas as n approaches infinity. So the limit as n approaches infinity of 1 minus n minus 1 over n squared times theta squared over 2. Well, the only thing that's relevant to n is this fraction in the middle here. So we get 1 minus theta squared over 2 times the limit as n goes to infinity of n minus 1 over n squared. Okay, and this is a standard exercise in calculus class. To compute a limit of a rational function, you take the leading coefficients, and their ratio is the limit. So that ratio is 1 in this case, so we're left with 1 minus theta squared over 2. Okay, so that's our new approximation to x, or cosine theta. Okay, which is better than than what we had started with, certainly. Okay. How about y equals theta minus theta cubed over 6 plus theta cubed over 6n squared? Same deal. You only have the n squared in the denominator of that last term. Okay, and there's no n in the numerator, so this is going to approach 0. So we're left with theta minus theta cubed over 6. And this is our approximation for sine theta. Great. We're already 2 terms into the Taylor series. And now is the really tricky part where we iterate. Okay, given that we have these better formulas for x and y, what happens if we use those for the yk's what will we see pop out? Okay, so let's start with plugging into x. If we take x equals 1 minus alpha times the sum of the y k's, okay, which is what we used earlier, then we can input our new approximation. Yk is theta k minus theta k cubed over 6, where theta k is k theta over n. And when we plug that in, and we're going to approximate alpha by theta over n still. When we compute this, when we plug in these values, we get this first equation, x equals 1 minus theta over n times this summation. This is our y1, this is our y2, and this is our yn minus 1. This is one part of our yn minus 1, and I suppose there should be a minus here. Okay, so we can take the cube terms and the linear terms separately. So if we take the linear terms separately, we get this, and that's just what we had seen earlier. So we don't have to worry too much about that right now, and taking the cube terms, we get this, all of the cube terms. So let me do this a bit more in an organized manner. So if we take this, and the similar terms, we get this part of our summation. And if we take this, and these cubes, we get this part of our summation. Okay. And this goes to the very simple formula, 1 minus theta squared over n squared times the sum of integers k from 1 to n minus 1, plus theta to the fourth over 6n to the fourth times the sum of cubes. And we have formulas for these. Great. And those are 1 minus theta squared over n squared times n minus 1 over 2, minus theta to the fourth over 6n to the fourth, n squared times n minus 1 squared over 4. Okay, if this looks a little different than the summation formulas you're used to, that's just because it ends at n minus 1. But taking the limit as n approaches infinity, again using the rules for limits of rational functions, okay, this term goes to theta squared over 2, and the final term goes to theta to the fourth over 24. Okay? And this is the first three terms of our cosine Taylor series. Okay, and we can also iterate for y. It's a little trickier. So we'll take y equals ny1 minus alpha squared times this summation, y1 plus etc. And we're inputting our new approximation. Yk is approximately theta k minus theta k cubed over 6. Okay, and theta k, again, is the k theta over n. So plugging that in, we get the equation you see below. And then we'll group our terms together. So if we take just this stuff, or rather, just this stuff, so everything excluding the cubes, that looks just like the approximation we did for y earlier. And when we had reduced everything, we landed at this expression. Okay, but then if we take everything that involves cubes, so this, etc., what we get is this summation. Okay, when you factor out the theta cubed over 6n cubed, you get this fraction in front, and the sum of cubes is what's left inside of the parentheses, or the sum of sums of cubes. Fortunately, Ibn al-Haytham's equation is useful again, and we can replace this sum of sums of cubes with the difference n times sum of I cubed, where I goes from 1 to n. Well, this should probably be n minus 1, and this should be an n minus 1 as well, minus the sum of the fourth powers. Okay, and in the previous lecture, we got formulas for both of these summations, and we can plug them in here and reduce. And what we end up with is theta minus theta cubed over 6 plus theta cubed over 6n squared plus theta to the fifth over 6n to the fifth times 3n to the fifth minus 5n cubed plus 2n over 60. And when you let n approach infinity, the leading coefficients of the numerator and denominator are 3 theta to the fifth, n to the fifth, divided by 6 times 60 n to the fifth. And so canceling a factor of 3, we end up with theta, as well as the factors of n to the fifth, we end up with theta to the fifth over 120, which is the first 3 terms of our Taylor series for sine. Some final thoughts to summarize. Ancient Indian mathematicians contributed some important innovations. Just think about 0. The school of Kerala improved trigonometric techniques for use in astronomy, and by iteratively approximating yk, then extrapolating to sharpen the approximation formula, Madhava was able to compute Taylor series for sine x and cosine x well before any of his European counterparts. Thank you so much.